Welcome everyone, and thank you for joining us today for our webinar titled Graph Embeddings for Graph Native Machine Learning. My name is Sabine Seitz. I'm part of the marketing team here at Neo4j. I'm joined today by Amy Hodler, Graph Analytics and AI Program Director, and Dr. Alicia Frame, Lead Data Scientist at Neo4j. We have pre-recorded the session to be on the safe side with the demo. Therefore, I'm excited that both Amy and Alicia are available to answer your questions throughout the webinar. Please submit your questions using the Questions tab located at the top of the screen. We will publish all answered questions and they will be visible to all of you. We also plan to answer questions from the audience at the end of the webinar, but if by any chance we don't get to answer them all, please mail them to webinar@neo4j.com. Also, you will receive a follow-up email with the links to the slides and the recording. And with that, I'll go ahead and hand it over to Amy.
Great, thank you, Sabine. Thank you, everybody, for joining us today. We have a fun demo to go through, but before we get to that, we're going to spend just a few minutes talking about graph data science in general, then the graph embeddings that are in Neo4j themselves, a little on a really cool machine learning model catalog as well in Neo4j. Then we'll go through a demo and kind of wrap up how that all gets put together. So to start with, it's nice to do a little level set on, well, what do we mean by graph data science? And in general, if you think about graph data science, if you're familiar with data science, where you're trying to answer questions with data, this is kind of the same thing, only you're using relationships. So, as opposed to just crunching, traditional numbers, you're looking at the relationships between things. Maybe you're using graph algorithms to do analysis, feature engineering, doing queries to understand what's in your data, data exploration with graph visualization. All of these things come together in a multidisciplinary workflow, which we call graph data science. So again, just trying to answer questions using the relationships within your data itself. So the other thing that I like to talk to people about is, like, why do I need graphs to make my data science better? Why do I need graphs to make my predictions better? And the really exciting thing is that you can use the relationships that you already have in the data that you own and that you have to make better predictions. And what we see a lot is a lot of data science models ignore the network structure, ignore those relationships. But we know relationships are very predictive. They're very predictive of features. They're very predictive of behavior, and they can increase your overall accuracy. So, and we definitely see this when you combine graphy features and non-graphy features. We see predictive accuracy increase. We see reduction in false positives. So, and some of these predictions you actually can't attain without using graphs themselves, or some of these understandings. So if you think about something like understanding page rank, well, if you're not using graphs and graph algorithms, you can't understand the influence that PageRank is able to uncover, because you're not looking at it that way. And so one of the things that we also say is that combining these with current workflows makes a lot of sense. You don't have to throw out what you're already doing. If you have a machine learning pipeline, include the relationships you already have, include those with the features that you're already creating and with the models that you're already creating with different workflows. So you don't necessarily have to do everything differently, but this is a way you can use relationships to increase the accuracy and the reduce any false positives you might already be seeing in your work. So we are also working with many customers that are doing this live. So it's not just something that we're doing and we're talking about. So we have customers across different industries that are using graph data science to improve what they're currently doing. One, AstraZeneca, that many of you might be hearing about today, but we are working with them on a project to look at patient journeys. So they're using graph data science to try to look at how you can do early intervention with these more complex diseases. So if you think about complex diseases that evolve over time, what they were doing is trying to look at 3 years worth of visits, look at the different tests, look at the different doctor visits they might have, look at diagnosis and how those evolve over time, and taking a look at tens of billions of records and trying to find similarities in the patient journeys. So if you can think about a journey of a patient, and how things evolve over time, can we look at those journeys and then try to understand which ones are trending in one direction or another direction, and then trying to use ways to identify communities and using graph algorithms to find the best intervention points. So how are journeys similar? How are they dissimilar? And what can we use those understandings to then intervene sooner and get better long-term patient outcomes? Another customer, Meredith, is doing what they call, marketing to the anonymous, or what they originally called marketing in the dark. They were having trouble with a lot of anonymous users across different devices, and cookies that would change and evolve and decay very quickly. And they started with over 4 terabytes of data, which included over 4 billion nodes and 20 billion relationships. So a lot of information that they were trying to track and understand, but without having personal identifiable information, it was hard to know, how do we recommend new things to these people on our sites? So using community detection and graph data science, they were able to actually develop over 160 million rich, very unique profiles. And so you can imagine having these unique profiles with a lot of information, but without that personal information itself. So still keeping it anonymous, but we understand something about these users. Maybe they have a tendency to prefer outdoor magazines, or maybe magazines about or articles about cooking. And using that kind of rich profile, they were able to increase the visits by over 600% of anybody with those profiles they were able to create. So very good results from using the Graph Data Science library. And then another example with an anonymous customer is a top 10 financial bank. They were looking for fraud, in a particular credit card fraud. And in this case, they were missing, not quite, almost 70% of their credit card fraud because of synthetic identities. And so that's where you're combining real and fake information. And they had about 1 billion nodes, about 1 billion relationships, needed to analyze those, look at patterns, look at communities. And so using both traditional queries, graph queries, and graph algorithms together, they were able to find tens of millions of fraud in under a year. So very real world results looking at combining graphs with the predictive processes they already had. So when we look at how customers go through and use graph data science, there's a natural evolution that we see most all of our customers go through. First is just getting that domain information together in a knowledge graph and understanding what's in there. Maybe you're making queries to understand the nature of your network itself, where the influential points are. You're trying to match patterns you already know. Maybe your domain experts are using that to support decisions they have to make. And then very quickly after that, they're trying to look at analytics and understand patterns where you don't know exactly what you're going to get, but you know the pattern you're looking for. So an example would be a graph algorithm like PageRank that I mentioned. So you're looking for a highly influential person or item in your graph, but you don't know what that answer is going to be yet. And then with graph feature engineering, you're using that information, whether it's from an algorithm or a query, and you're creating a predictive feature you can then use in a machine learning process, whether inside or outside of Neo4j. Graph embeddings you can think of, and we're going to talk more about them, as kind of an advanced or nuanced form of graph feature engineering. So in this case, you are trying to represent the structure and certain areas of the structure of your graph, so you can then use that for some kind of machine learning itself. And then that takes us to graph networks, where you have graph native learning, and where you're starting and ending with a graph, but you're also trying to understand even more nuanced predictions and features, and doing that within a graph structure itself. So this is kind of the evolution that we see. And if we kind of just step through a few of those, we can kind of see with the knowledge graphs, you might be doing simple queries for, in this case, we have a fraud example. And I often call these deceptively simple queries because you might be looking at something like, how many flagged or fraudulent accounts are in a new applicant's network 4 hops out. And you might want to do that to process credit applications or some kind of approval process. And so you may need to very quickly look at a few hops out, 4 hops out, and that can be very difficult with a traditional relational system because of all the indexes and joins and lookups you would have to go through. So you can add these kind of metrics to your approval process. Very simple way to take a look at what you have, but what you're looking for. You're looking for, in this case, flagged accounts, or it could be something like account variables in common, something like that, but what you're looking for. And then you can very quickly see where you would want to expand that and maybe use something like graph algorithms. And so we know we want to use graph algorithms to understand network structure. We want to reason based on the network structure. A couple graph algorithms that we see used a lot in fraud would be something like connected components. And that's where we're trying to look at disjointed groups, in this case, sharing identifiers. A lot of times they look like floating islands, and that can be very predictive of fraud. Another algorithm we see used a lot is PageRank. And so all of you that are familiar with PageRank know that that's all about understanding influence. And in this case, we're also using it as a stand-in for transaction volumes as well. And you could use personalized PageRank to say transaction volumes of one kind of merchant is certainly appropriate, but transaction volumes that are super high for another type of merchant might not be appropriate. So you can also use that to look at different types of transaction volumes. Louvain, a community detection algorithm, is looking at communities, in this case, that have a lot of frequent interactions, and interactions that are more frequent than with each other than outside of the group. And that may be indicative of fraud or something you want to look farther into. Another simple algorithm is Jacquard similarity, node similarity, where we're looking at similar accounts. So let's say you have an account or an account profile is fraudulent, or a fake profile that has fraudulent commonalities, attributes. And then you could say, well, what top 80% similar nodes are there to this fraudulent profile? And then you could look farther into that as well. So different ways you can use graph algorithms to look for patterns that you just don't know what the results are going to be yet. And then the other, moving on to the next section would be graph feature engineering for fraud. So think about those queries that we just showed you and those algorithms that we just looked at. And you'd want to combine and process data to create new information that's even more meaningful. And so in this case, we're going to look at graphs and look at influential people that also share identifiers. And in this case, you can run your graph algorithms, you can run your queries, you extract those out into a form. In this case, you can see the numbers and the labels that we have in the little chart, but you can extract those out into a format that can then be used in a machine learning process to improve based on your training data and improve your predictions in that way. And then after graph feature engineering, as I mentioned, you have people wanting to move into graph embeddings for feature engineering. So like I said, a kind of a nuanced way to look at feature engineering, you're able to do more. And in this case, instead of running multiple algorithms and different queries, where I think in the last we were looking at betweenness, centrality, and shared identifier, but you might run many, many different algorithms trying to figure out which one is very predictive for you. And if you don't know which one you need to run, you can instead describe an aspect of your graph structure. And then embeddings can learn that representation for what the problem that you're looking for. So I think something Alicia says a lot is with a graph embeddings, you're using the embedding to learn the structure for your specific problem. So depending on what your problem is, the graph embeddings, you can use the graph embeddings to learn a structure that can then be predictive. And as you can see here, you can see where if we were to represent the entire graph, there's a little matrix there with a lot of zeros and ones and many pretty colors, that if we were to abstract that out completely, you would have an amazing, rows. You might have like 64 by 64 rows. I mean, that would be a simple graph embedding if you were, or graph representation if you were trying to represent every single thing in your graph. But instead, with the graph embeddings, it extracts just what is more predictive, what is significant for your problem, and so really collapses it down into a lower dimensional representation, so you can then extract that out much more efficiently and use your machine learning there. So with the graph embeddings, that kind of walks us along into the evolution of graph data science that we see people moving to. With Graph Data Science version 1.4, we're actually we've included graph embeddings, and we're moving just beyond that as well. So we are starting to dip our toes in the graph network space as well, where we can do graph native machine learning. And so we're kind of excited to talk about that more today. And the four things that I would say are kind of the key evolutions in GDS 1.4 that give us the graph native machine learning. First and foremost is the graph embeddings themselves, where we're actually using matrix math and neural networks to learn that structure, that representation of your graph itself, so you can then use it in other machine learning tasks. We've also included a model catalog, because if you're going to train on your graph and create your graph embeddings, you want to also be able to store and fit predictive models, and do that within Neo4j itself. We've also included a machine learning algorithms category, and in this case, KNN is our first one, which Alicia will talk to us more about. But including that, so we can actually then make predictions based on the model that we've trained and that we've trained using the graph embedding. So it kind of flows us through that process to actually make those embeddings useful and be able to make predictions. We've also included more information and more full featured around our graph Pregel API, so that people can write their own algorithms and implement them within Neo4j, or use algorithms that they've implemented in other systems and now want to use them in Neo4j as well. So those are the big things with GDS 1.4. Why do people care about that? If we're really excited about it, if it's not clear why you might be excited about it, first and foremost for me, this gives people a new way to do learning. And we've got graph-based machine learning. Previously was only accessible, I would say, by researchers in a very few very advanced companies like your Facebooks and your Googles out there. So giving people a way to do graph native machine learning in a commercial tool that's accessible, I think is a big deal for people, because you can uncover things that you didn't even know to look for, that you weren't sure even which algorithm to choose, because it's, nothing seemed to fit. It may eliminate plateaus when you're using traditional algorithms or graph algorithms that you're familiar with, but you weren't getting the same predictive quality, or you want to improve that beyond maybe what you're already seeing. And then, of course, writing your own algorithms so you can tailor and customize things to your own needs. The other thing that I get excited about is small data and incomplete data, or rather, I get excited about helping out with that area, because that's something we hear a lot from customers. Is this year's been a lot of change. The data that I've had in the past is no longer valid. How do I deal with this either incomplete data or just small data? I just don't have a lot. And that kind of goes back to the slide about adding features, adding better predictions with the data you already have. So graph features based on existing data improves machine learning results. That's always been the case when we see that combination. I think it's now more important than ever, because a lot of our historical data has become less accurate. It also allows you to create graphs, new graphs, using synthetic relationships. So you can simply, with a list of nodes with properties on them, you can create a graph just simply from a list of entities with properties, which is kind of exciting. So you can add those synthetic relationships. You can also complete your graph along the same lines using some of the similar methods. Complete your graph, do predicting of missing graph data, with the machine learning algorithms within Neo4j, you might be predicting missing links. You might be predicting information about your nodes, like labels that you don't currently have. And then finally, the other thing that people are excited about is this idea of continual learning and enhancements. So if you think about it, being able to continually make predictions about new graph data as it's added is pretty monumental. Hasn't been done before, and you don't have to retrain your model each and every time. Alicia will explain how that's possible when we look at the demo and we look at GraphSAGE graph embeddings. But this allows you to continually enhance the value of your graph database as you're adding in new information and you have new results as well. And just in general, having those supported graph embeddings, a model catalog in a graph framework is pretty unique. So those are the things that people get excited about. I hope that gives you a good kind of baseline. And I think Alicia is going to tell us a little bit about the graph embeddings.
Awesome. So hopefully Amy has kind of gotten you all up to speed about why do we care about graph data science? Like, what are we talking about? Why is it important? You know, what's the there? And so my portion is really going to be doing more of a technical deep dive into, like, you probably keep hearing, oh, embeddings, and maybe you've thought embeddings sound really cool and useful, but I'm still not sure what they are. So I'm going to really spend time explaining what are graph embeddings, what do we offer in Neo4j, what's the ecosystem of tools around that to get you up and running and show value, and then switch over to a pretty cool demo of some of the new features in 1.4. So when I'm talking about embeddings, I really like this meme of the exploding brain to kind of compare and contrast embeddings with what you've done before. And so if you think about, you've used Neo4j before, you used a database. A query is really something that's human crafted and human readable, super useful. But what you're doing is you're going in and you're saying, find me this pattern and return to me the data that matches it. So in my example, I have, match a person who has an enemy and then an enemy of that second person, and then make the first and third person friends, because the enemy of my enemy is my friend. I wrote that query. I know exactly what it means, and I know what the results mean. So it's pretty bespoke pattern matching. The next level up in sophistication is we talk about the graph algorithms, and we've had those for a while. And what those are is it's a predefined formula that tells you something about the topology of your graph. So in my example, I have the formula for PageRank. That just is a predefined formula. It was invented by Larry Page. It's how Google worked in the late 90s. That says how important is every node based on the number of edges those nodes have and the number of edges their neighboring nodes have. And when I calculate PageRank, every node in my graph gets a PageRank. So in my example, I have a PageRank for our CEO, Emil. I have Amy's PageRank, and I have my own PageRank. And the results of PageRank are human readable. So Emil's PageRank is not surprisingly greater than mine. Emil is more important than I am. So it's a predefined formula, but the result is human readable. I know that a PageRank of 13 versus a PageRank of 4 means the person with a 13 is more important than a 4. So formula is defined, I understand the results. The final level, kind of the mind-blown step, is your embeddings. And so embeddings don't have a predefined formula. It's not for every node sum up how many neighbors it has. It's instead, you have a heuristic that says, this is how you learn the right descriptor of every node in my graph. This is how I learn the representation, by minimizing this loss function, by pooling this data. Basically, it's a computer-defined way of learning. And when you run your embedding on your graph, it learns the right representation for your data set. So it's really AI learned. And then the result you get is for every node in your graph, Amy kind of showed this before in the feature engineering example, every node gets a bunch of numbers that represent it. And so if I look at this, I see that there are 5 numbers representing Emil, 5 that represent Amy, and 5 that represent me. And I can tell as a human, well, those numbers are different from each other. But to me, just reading those, they don't make any sense. However, what those numbers do is they summarize everything important in that extended graph into the minimum set of numbers that help you reconstruct the data of your graph. So it's basically the AI learned formula of what's important in my graph, custom built to put into your machine learning algorithms. So as you kind of go up, it's human crafted and human readable with queries, then you have a formula and a human readable result with an algorithm, and then embeddings are machine learned and machine readable. And so let's talk a little bit more about what they are. So title of this whole talk, we keep saying embeddings, what are they? End of the day, what an embedding is it's a way of representing each node in your graph with a bunch of numbers. And so what that means is when you run an embedding in Neo4j, every single node in your in-memory graph that you've trained your embedding on gets a representation. And what's important about that representation is it's the same length for every node, and those numbers in that embedding preserve the key features of your graph, and they can reduce the dimensionality of your graph. So if you think about, I have a 5 billion node graph, and I want to do machine learning on it. When we talk about algorithms, it's like, well, I can run PageRank, I can run betweenness, I can run Louvain, and I can put each of those values into my ML pipeline. But what if the thing that's important and predictive isn't PageRank, and it's not Louvain, and it's not betweenness? Well, I don't know about it because I didn't run that algorithm. What the embedding does is it takes that 5 billion node graph and condenses it into the relevant information about every node. So if you think about, you have your 5 billion node graph. To represent it mathematically, you have a 5 billion by 5 billion adjacency matrix. And it's going to be for every pair of entries, is there an edge between node A and node B? And if you think about it, that adjacency matrix is going to mostly be zeros. And so you have this really big, really sparse data structure, which is not going to be possible to put into your ML algorithm. So what you do instead is you basically want to reduce the dimensionality of that. So instead of having 5 billion zeros and ones that describe every node, and that only describes who's a 1 degree neighbor, what I want is I want to have 5 billion rows, so one representation per node, but maybe I want the 20 numbers that summarize each node and what's important about it. And so the embedding itself is how you squish down those 5 billion zeros and ones into the right set of numbers that capture the extended topology of your graph. What's a neighbor? What's a 2nd degree neighbor? What's a 3rd degree neighbor? What are the properties? While preserving what's important about that node. So they have to be able to be decoded. So when you have an embedding, once I've generated an embedding for a node, the way I know if it's useful or not, and the way we train the embeddings to be produced, is once I have that representation, I have to be able to use it to decode and reconstruct the neighborhood around each of my nodes. So once I have node embeddings, I should be able to reconstruct whether 2 nodes should have an edge between them. Or once I have my embeddings, I should be able to decode what was the label of that node for that embedding. And so the idea is embeddings represent each node in your graph in a low dimensional but highly informative way. And just as a footnote, there are different types of embeddings. What Neo4j offers are node embeddings. You may have seen in other places whole graph embeddings, path embeddings, edge embeddings, and different embeddings use different techniques. But what we're talking about Neo is node embeddings. And this is my cheat sheet. This is like if you don't want to read the docs, if you want to zone out and you're just like, what does Neo4j have for me? We basically have 3 techniques. We have fast random projections, or FastRP, which is a linear algebra based technique. We have Node2Vec, which is probably the most well-known embedding that's out there, which is based on random walk sampling, and then you train a neural network to represent your graph. And then we have GraphSAGE, which is based on a graph convolutional neural network, and it creates an inductive predictive model. And if you're kind of like, which one should I pick here? It's the easiest way to think about it is, what do I need to represent? If your graph has node labels, so it's a multipartite graph, and it has node properties, you probably want GraphSAGE because that's intended to use properties as well as labels. If you want something lightning fast, FastRP is where you start. And if you want something that's interpretable, and if you want something that's easy to wrap your head around, Node2Vec is a good place to start. It doesn't support weights, it doesn't support properties, but it has really interpretable hyperparameters. So this is kind of your cheat sheet of which embedding do I want. And I'm going to go through each of these in a little more detail to explain how they work and what they tell you. So I like to think about Node2Vec and FastRP together as kind of compare and contrast. So both of these are direct node embedding techniques. So what that means is they learn the embeddings, and then each node in your graph gets an embedding. If you want to generate embeddings for new nodes, then you're going to have to rerun the embedding. Both of these give you fixed length vectors. Here's a bunch of numbers for every node in my graph. The way Node2Vec works is for every node in your graph, you're going to take a random walk through the graph from that node, and you're going to take a fixed number of them and build up context around those nodes. And basically what you do is then you train a skipgram model, which is, if you've ever used Word2Vec, the idea is in Word2Vec, given a word, what should the next word be in a sentence? In Node2Vec, it's given a node, what's the neighboring node? And you train the skipgram model and you pull out the hidden layer, and that's your embedding. Node2Vec is pretty easy to understand, which is why a lot of people like it, right? I can explain it in 3 sentences. You probably followed that pretty easily. And the parameters that you want to tune make sense. It's basically how many walks do I take? How far away should they go on the graph? Should they stay close or go further out? Pretty easy, right? And there's lots of examples. The challenge with Node2Vec is it's pretty slow. If you have a billion node graph, unless you have a crazy number of threads, it's probably not going to finish. And so the alternative in this space is FastRP, or fast random projections. And what FastRP is it basically uses linear algebra to construct a similarity matrix between each node in your graph. So if we go back to that 5 billion node adjacency matrix, you construct a similarity matrix that says for every pair of nodes, how similar are they? And then you multiply it by what's called a random projection, which is basically random numbers generated from a very specific distribution that's intended to preserve the distance between pairs of nodes. You multiply those two matrices, and then you get a dimensionality preserving lower dimensional representation. And that is a little harder to wrap your head around. It's some beautiful math. Node2Vec is actually an approximation of what FastRP calculates directly. The cool thing here is that FastRP is 75,000 times faster than Node2Vec with equivalent accuracy when you've tuned it appropriately. So FastRP has a lot of parameters that you have to tune, and they don't make as much sense. They're not how far away in the graph should I go. They're things like, well, how many iterations do I want, and what do I weight each iteration with? And they're not quite as intuitive. So usually when you're using FastRP, you're going to be doing more tuning, more adjusting to make sure that your results make sense. But one cool thing you can do is you can run Node2Vec on a small subgraph till you get a result that makes sense, and then tune FastRP to reproduce those results. However, the idea for both of these is you get a direct embedding, every node gets a value, and when you get new data, you have to rerun them. So even though FastRP is much, much, much faster, maybe you don't want to retrain all the time. And to address that, we talk about using GraphSAGE. And so what GraphSAGE is this is a different approach. Instead of giving every node in your graph an embedding, a number, GraphSAGE gives you a predictive model that given a node and given its neighborhood, it can predict what the embedding should be. And so what that's called is it's an inductive model. And so what GraphSAGE does is it takes your graph, it samples the neighborhood around each node in your graph, and GraphSAGE is built to use properties from your graph. So it uses both the neighborhoods around your nodes as well as the properties of those nodes in order to fit a loss function that can then reconstruct the embedding for any new node and any new data set. And so what you're doing is step 1 is sample. So each node in your graph, you take your random walks, you figure out what are the neighboring nodes. Once you've got those random walks, GraphSAGE is built to use properties. So you aggregate the properties from those neighboring nodes to build up kind of a concatenated feature layer of what are the properties of my neighbors. And then you predict, where you basically fit a loss function that says, given my neighboring nodes and their properties, let me come up with a model that makes nodes that are close to each other in the graph similar and further away from each other in the graph different. And basically the idea is that a GraphSAGE embedding should be able to reconstruct these nodes are close together in the graph, these nodes are further away, using both topology and properties. And so to dive a little bit more into that prediction step, the idea is you're fitting a function for your graph, meaning the topology of your problem, as well as the properties on your data, that minimizes the distance of nodes that are closer together in your actual graph and maximizes it for those that are further apart. And at the bottom, we actually have what that loss function is. The important thing is it transforms the aggregated data into an embedding that can represent the structure. And so once you fit that loss function, now you have a predictive model. So you can put in new data, fit it into that loss function and come up with a new embedding. So the idea is I've trained my GraphSAGE model. It's pretty computationally intensive, so that might take a while. I add in 10% new data into my graph. Instead of, oh no, I have to run it all over again, throw everything out, I can actually take that predictive model. I can sample and aggregate the properties of the neighbors of those new nodes I've added in, and then I can make a prediction and generate those embeddings without retraining them. So the idea is, as I add in data, I can automatically generate the embeddings for them without relearning, which is pretty important. And then kind of cool, I have embeddings. You told me they're not human readable. So who cares? The idea is once you've got your embedding, you can do a lot of cool things, a lot of kind of traditional ML tasks. So maybe I want to do neighborhood prediction, right? I want to do link prediction on my knowledge graph. I want to know where should there be an edge. I can take that embedding and I can use it to predict what nodes are neighbors of each other, which nodes should have edges between them but don't. You can also use it for classification. So let's say you have a graph where you're missing data. You have a transactional graph for fraud, and you have these accounts are committing fraud, these accounts are, and these accounts I don't know. Once I've trained my embedding, I can then run a classification model that says, based on the embedding, should this new node be a fraudster or is it a neutral node? I can predict the labels. And then you can also do visualization. So maybe you want to understand what are the clusters in my data. I can train the embedding. I can then use something like PCA to reduce it to 2 dimensions, or I could do a t-SNE plot and I can start to see in 2-dimensional space, how is the data in my graph distributed? So graph embeddings can be used for so many different things. They're really kind of foundational to your sophisticated ML pipeline. So how do we make GraphSAGE work, right? Because I'm training a predictive model. And the exciting thing here is this means that we now store machine learning models inside Neo4j. And I got my meme in here. I've got my animated GIF, so I'm happy. What does that mean? So if you've used Neo4j for a long time, often you'll hear us talking about models, and we mean data models, like what's the architecture of my graph. For machine learning models, what we're talking about is actually predictive models that say, given this data, predict what the result should be. And so what GraphSAGE is doing is you train a model to predict node embeddings for unseen parts of the graph or new data. And once you've trained this model, it's going to live in the analytics workspace in a model catalog. So in the past, we've talked about the graph catalog. So I've got multiple graphs loaded into memory. I can run PageRank on different graphs. What you can do here is I have a model catalog that contains all the models I've trained and the versioning information. So what data was this trained on? When did I train it? What's the name of the model? And then I build those up in my model catalog and I can apply them to data. So if you're a Python user, maybe you've used scikit-learn a lot, you're probably familiar with, rfclassifier.fit, model.fit, and then model.predict, right? You train your model and then you make a prediction. The equivalent in Neo4j using the model catalog is you train your model with GraphSAGE.train, and then you tell it the name of that model. When you want to make a prediction, you say GraphSAGE.stream or .write or .mutate, and you pass it in the data that you want to make the predictions on. So in this case, it's a new graph, and the name of the model you want to use. And so the difference here is if you're kind of a Python user, maybe you're generating pickle files all over the place and you have to know where you left them. You have to look in your file directory or scroll up in your code. Neo4j is a database, right? So we have a catalog that tracks all of your models to make it easy to say, oh, I trained 3 models. I want to use this one. I can call them up. I can look at them. I can introspect their properties. So pretty exciting stuff. And then the third piece of the puzzle of, cool, I've trained an embedding. I know how to access it. I've got my model catalog. What do I do with it? And so we really want to make it possible to do that full life cycle in Neo. And so in 1.4, we added a new algorithm called k-nearest neighbors. And what this is it's basically a machine learning model for similarity. So it compares the properties of nodes in your graph to find the k most similar neighbors. And if you've seen this before, maybe you've tried to run node similarity on every node in a very large graph. And maybe you've posted on the community forum or filed a Zendesk ticket and you've had me say, no, you can't run node similarity on a giant graph. KNN lets you do that. So what it's doing is it's constructing a graph based on properties. It could be embedding similarity, it could be node properties, Or it could be just disconnected data where you don't have any edges, but every node has a bunch of properties. And what you want to say is, using cosine similarity, how similar are these nodes to each other? And KNN is an approximation algorithm that uses gradient descent to build up your nearest neighbors network with about 90% recall, and it's pretty fast. So a user specifies, this is the sampling rate, this is the number of iterations I want to have, and KNN reconstructs your graph based on your embeddings, based on your node properties, to say where should the edges be based on these representations. So it lets you train your embedding, then make use of it all within Neo. And so with that, hopefully that gave you some kind of foundations for what I'm talking about. And now I'm going to switch over to do a quick demo to walk you through what this looks like in practice. So let me share my screen. And hopefully you all can now see, I've got Neo4j browser pulled up. And I'm going to just walk through loading a graph into memory, training GraphSAGE, demonstrate what the model catalog is, using a new technique called collapse path to project a monopartite graph, train FastRP to show you kind of comparing contrasts and speeds, build up my k-nearest neighbors graph, and then demonstrate the results in Bloom. So the first thing I like to do is kind of start off with the graph schema. You probably have seen me use this in demos before. This is just a transactional graph. So I have customers who are making transactions, buying items, the items belong to categories, and the customers live in countries. And I like this example because there's a lot you can do with it, and we all kind of understand this data model, right? So the first thing I want to do is I need to load a graph into memory. And so what I'm going to do here is I'm going to show this to you. I'm creating a what I'm calling the retail graph. And because I want to run GraphSAGE and I want to demonstrate that it can use multiple labels, so multiple node types, and it can use properties, I'm going to load a lot of stuff into this graph. So the first thing I'm loading is I'm talking about items. And the properties that I want to load for my items are the price of each item in my graph, the quantity sold of each item in the graph, and the stock code. So these could be predictive for my embedding. And then I want to load the transaction nodes. So remember, items are a part of transactions. So I'm going to load in my transactions, and then I'm going to load in the time stamp of the transaction and the transaction ID. And then the last thing I have to run is basically relationships. So I want transactions contain items. I'm going to load that into memory as well. And I'm going to project my subgraph just for this. And I cleverly loaded this up while I was talking to you. And you can see this loaded pretty quickly. I've got 22,000 nodes in memory, just short of 1 million relationships, took 430 milliseconds. And I can see all about, what have I loaded in here? And it's exactly what I explained before. So the next thing I want to do is I want to train GraphSAGE. And I'm going to kick this off running and then explain it. And so what training GraphSAGE looks like is I'm going to tell it, here's my GraphSAGE algo call. So I call beta.graphsage.train. And I pass it the retail graph that I loaded into memory. I'm going to tell it to train a model called GraphSAGE multipartite demo. And I'm going to tell it which features I want to use. So the features that I want to use today are the ones I loaded in. So the price of the items, the quantity, and the stock code, all belonging to items. And then I want to use epoch time and transaction ID from my transaction nodes. And what's smart here is it actually knows that I've loaded 2 different types of nodes, right? I have items and transactions. And what it's going to do is it's going to pad, it's basically going to one-hot encode the node labels, and then it's going to pad the feature vectors that represent those properties. So I need to tell it that I have a projected feature dimension of 7. And this is something you would probably tune in the real world. But the way you start here is I basically say, well, I've got 2 labels, I've got 5 properties. Let's go with a projected feature dimension of 7. I'm going to tell it I want to use degree as property. So this is basically saying also use the number of edges every node has to predict my embedding. I'm going to tell it how far out in the graph do I want to look and how many times should it train. And so I'm going to close this because this has been running in the background while I explained it. And you can see here that it took about 6,500 milliseconds to train, so kind of about a minute. And what I've done here is, so there were max iterations of 10. I used a sigmoid activation function. I used the mean aggregator. And you can see all the information that I put into training my model. And what's cool is now that I've trained this model, I can go ahead and I can look at it in the model catalog using gds.beta.model.list. And this one is fast, so I'm not going to run it in the background. And you can see that, okay, in my model catalog, I've got my GraphSAGE multipartite demo. It tells me everything that I did when I trained it. And then if I scroll over, it also tells me when I created it. So if I was running a bunch of stuff, it would be useful for keeping track of, oh, I trained 5 different models. What did I train them on? And so the next thing we can do is we can actually pull back, what is an embedding? And remember, I said this is, it's machine readable, so it's not super exciting to look at, but I like to kind of peek under the hood. And this is a little slow, not because it takes forever to calculate, but because it takes a while to render all these numbers in the Neo4j browser. So what I'm doing now is I'm telling it, okay, stream my GraphSAGE model results. So remember I said I train my model. It's called GraphSAGE multipartite demo. Now I pass that to GraphSAGE.stream and I say, use that model on my retail graph to give me embeddings. And so what I see here is for each node ID, I get an embedding that represents that node. So I have a bunch of numbers that GraphSAGE learned that represent each node in my graph. And I can see like all my nodes have different embeddings. Cool, but not useful to me as a person. So what I'm going to do now instead is I'm going to add these embeddings to my in-memory graph using the mutate function. And so what this does is I've already loaded my retail graph into memory. I'm going to say use my GraphSAGE multipartite demo model to add a property called embedding to my in-memory graph. And this happens super fast. And now I've got kind of my results from GraphSAGE all loaded up. Now what I want to do is I want to compare and contrast, because this is a demo. I want to kind of show the difference between FastRP and GraphSAGE. So now I've got my FastRP results. I'm going to switch a little bit and I want to use FastRP. So FastRP is intended to run on a monopartite graph, which means one node type, one relationship type. And if you remember, the graph I loaded into memory has items and transactions. So that's 2 types. So what I'm going to do is I'm going to use this new algorithm that we introduced in this release called collapse path. And what it's going to do is it's going to take items that are connected to each other based on a transaction node. So you have item contained by transaction contains another item. I'm going to say, okay, I want you to collapse all of that graph together. So it's an item to item graph based on traversing 2 contains relationships. And so I'm going to, instead of using a cipher projection, I'm going to reshape my graph on the fly. I'm going to put a new relationship in memory called bought together. And so I'm going to run this. And if you've ever run a cipher projection before, they're pretty slow. What this is going to do is that collapsed my graph almost instantaneously. And what you can see now is I've created just about 90 million in-memory relationships between those item to item nodes. And you might be like, oh dear, this is going to set her laptop on fire. The good news is that FastRP handles big graphs really well. So I'm going to tell it, I want to run on the retail graph. I'm going to just run on the items, and I'm going to use this new bought together relationship I loaded into memory. And I'm going to use, this is FastRP extended. So FastRP doesn't use properties, but FastRP extended lets you use properties. So I'm going to tell it, actually, I want to use price and quantity. And I'm going to tell it, I want each embedding to have 10 numbers. And I'm going to tell it my property dimension is 4. This is another thing that if you were doing this in the real world, you would tune. But a good starting point is kind of 2 times the number of properties, and it has to be less in your embedding dimension. So I have 2 properties, price and quantity. 2 times 2 is 4. That's less than 10. I'm good to go. And then I'm going to write my new FastRP embedding to my graph. And so I kind of cheated before when I was talking about GraphSAGE. I'm not going to cheat now. I clicked run. It's written a node embedding to every item in my graph. It completed after 635 milliseconds. So FastRP, lightning fast. Then what I want to do is I want to actually use these embeddings for something. So I'm going to train k-nearest neighbors. I'm going to tell it, first, I want to build a nearest neighbors graph using my GraphSAGE embedding. So I'm going to take the top 3 nearest neighbors based on the GraphSAGE embedding. I'm going to create a new relationship that's called similar GraphSAGE embedding, so I can see which nodes have the most similar embeddings to each other. Then what I'm going to do is I'm going to also use my FastRP embedding, and I'm going to create a similar FastRP relationship. Pretty simple, and then I'm going to kind of compare and contrast the results. So I'm going to run this, and you'll see it's pretty fast. Again, we talked about why KNN instead of node similarity, much, much, much faster. So I created all these new relationships. Now I'm going to go over to Bloom to kind of show you what the results look like. So now that I'm in Bloom, I've got something pulled up from before. So I'm going to log back in, and I will clear my scene. This will just take 1 second. And this is what happens when I spend too long explaining my demo. But all it's doing is connecting to my database and probably trying to reconstruct whatever I had open before. I'm going to just make a new scene because I don't know what I had open before. What I want to do is I want to just look at an item in my graph to see what it looks like. So I'm going to look at my Space Owl item. If you've seen me do demos before, this is a fun one. So Space Owl is an item in my retail graph, and I can explore what are the neighbors of Space Owl. And so I can see which nodes have similar GraphSAGE embeddings. And so what I see here is I have one transaction and I have one item. And remember, GraphSAGE, we trained on both transactions and items. So this makes sense. And GraphSAGE learns what's close together in the graph. So I have probably a transaction that contained a lot of Space Owls, as well as an item that's probably in a lot of other transactions with the Space Owls. If I want to kind of compare, I can look at what has a similar FastRP embedding. And so FastRP is just trained on, just items. So the only similar FastRP embeddings I get are items that are similar in the embedded space, just with that embedding. So that's kind of, okay, this makes sense. So the next thing I want to do is clear my scene, and I can actually look at my similar embeddings. So if I go in and I look for similar FastRP embeddings, I can go in and pull back a bunch of nodes that are similar to each other based on their embedding. And there's a lot of stuff here. Basically, I can zoom in and I can see all of these items are similar in the embedded space. So FastRP learned that this ceramic strawberry is similar to the vintage red mug based on that in-memory bought together graph. And what this probably means is ceramic strawberries were bought with vintage red mugs a lot, as well as the ceramic strawberries were bought with this vintage bag. So if I clear this, I can instead look at, let's look at these similar GraphSAGE embedding. And what does that look like? And so what I can do now is I can see, okay, first things first, GraphSAGE embeddings learned similarity for both items and transactions. I can go in and I can see I've got my crochet bear. It is similar to a set of 10 cards, as well as a bunch of different transactions. So first check, okay, this makes sense. I learned both transactions that are close in the graph, probably they contained crochet bears, as well as items that were similar in the graph, probably based on their properties. So what I'm going to do now is I'm going to clear my scene again, and I'm going to do just one more quick check of what I've done. So I'm going to look at finding transactions that are similar to each other based on their embeddings. And kind of what does that look like? And I've saved a search phrase ahead of time so that it's kind of easier to pull back. And this is basically a Cypher query that says, find me embeddings, find me transactions that have similar embeddings and items that have similar embeddings. And so I can see I've pulled a lot of stuff back here. And I've got transactions that are similar to each other and the items they can contain. And sanity check, this seems to make sense, right? These two transactions are similar and they contain the same items. I'm going to switch this over to a hierarchical layout, which makes it a little easier to kind of look at these clump by clump. And what I can see is that I've got two transactions that are similar to each other and a bunch of items that they contain in common. And what I can do here is I can go into the items and I can learn a little bit more about them. So this is a card holder. I sold 176 of them. The average price was $3.50. If I go in and I look at my wooden tree, I sold 349 of them. So I sold a lot of this one and I can see it's about 50 cents. And I can go through and I can start to say, does this make sense? So what I've seen is these two transactions are similar to each other in the embedded space. And then sanity checking those results, okay, they contain a lot of the same items, and those items have similar prices to each other. So what you can see is I've done link prediction on my graph. So which transactions look most similar, which items look most similar, and I've kind of sanity checked it. If I wanted to take this further, maybe I'm doing recommendations. So maybe I want to use this similar embedding to say, okay, I bought this white Christmas thing. I want to find the similar fast RP embeddings, so which items were most similar to it. And then what I want to do is I want to make recommendations based on which items are most similar in my fast RP embedding. So I can kind of compare and contrast, mix and match. I'm going to hand it back to Amy to kind of wrap us up.
Thank you, Alicia. And I'll go ahead and take over slides. Here we go. All right, so let's put things together as far as what you just saw. So an example, so Alicia just kind of walk you through is one example, and it kind of follows this format and this example workflow of kind of knowledge graph completion in this case, but you can kind of walk through the different steps. And what's different with what we're showing now is that you can do these steps within Neo4j. If you've seen us go through other demos where you go outside to do some of your machine learning, as Alicia showed you just a moment ago, you can do these all inside Neo4j now. And basically, you can start with just getting your knowledge in a knowledge graph and shaping it. In this case, we were looking at data sources that you could mine of, I think we were looking at research data sources and using NLP to actually construct your knowledge graph itself. And then you would use some of those queries and graph algorithms to basically do feature engineering. Maybe you have a domain expertise is trying to match something specific, or perhaps you're looking at between a centrality or specific community detection where you're going to write back some kind of features related to that. And then you might actually be doing your extraction on that information or grabbing that information so that you can then write back to the graph and have your features written to the graph. And then in the next step, you might be looking at the embeddings, which is what Alicia focused on. So in this case, you saw, or in this just a moment ago, you saw Alicia do several different types of embeddings in different ways to actually use the embeddings to then actually infer some relationships as well. And you can train those and create those machine readable representations, store those in your graph itself, or store it in, in memory until you're ready to actually save those back. And then what you saw Alicia do finally is to actually apply those train models to make predictions. And so you saw her kind of walk through both to use either collapse path, which was really interesting as well. So you can use them to make predictions about relationships, and then you can collapse those as well if you want. Then she looked at updating. You could update your original graph, or you can do visual exploration, or do both. And so you kind of saw her kind of walk through those different steps. We took a look at Bloom, and then you could throw out the results if you weren't happy with them, or you could update your original graph and kind of start that process. So one of the things that I think is interesting, about this is if you are doing graph-based predictions, you can now do them all inside of Neo4j. So you can keep your graphy predictions in making predictions about relationships, categories, whatever that may be, and you can keep that all inside of Neo4j. Or if you want to export them out to another tool like scikit-learn or Spark MLlib or something like that, you can also do that as well. So lots of different functionality, and this is definitely a very iterative process as well. And I think looking at time, I'm actually going to go ahead and skip us to the end and just show you a few resources that we have as well. And so if you're wondering about, how to get started, we have a lot of online resources for you. There we go. I'll show those to you. There's some guides on the developer site on Neo4j. GitHub, you can grab a lot of information and grab the Graph Data Science library as well. There are several books as well. If you're a developer, the O'Reilly book on graph algorithms is a really nice starting point for concepts. The last chapter talks about machine learning and gives you an example there. And then there's also a graph data science for dummies book as well, if you need to pass along information to, let's say, a manager or somebody who's not as familiar with graph data science. Is a good kind of starting point for them. So with that, I think we have time for 2 questions, or hopefully two quick questions, and they're ones that we hear a lot. And so I wanted to be able to just ask, Alicia, we hear this one a lot, is, hey, you've used the term neural network. You've talked about Neo4j and GraphSAGE. Are we providing a graph neural network in Neo4j?
That's a really good question. It's one that I like answering. So GraphSAGE itself uses a graph convolutional neural network to learn the structure of your graph for the embedding. So GraphSAGE uses a graph neural network in order to give you that predictive model that you use to infer your embeddings. What we don't offer is kind of like a generalized framework for any neural network. We're not rebuilding TensorFlow or Keras in Neo4j. Really, what we're doing is kind of front and center, doing graphy things in the graph, letting you use graph neural networks where it makes sense to, but making it easy. So we don't want you to visually draw out your whole network super painfully. Here's my hidden layers, I'm gonna connect everything up. What we want to do is we want to make it easy. So GraphSAGE uses a graph convolutional neural network to give you the right embeddings. We don't offer kind of a generic framework. If you want to kind of build from scratch, TensorFlow is great for that. We want to help you do graphy stuff in your graph with your graph data.
Awesome. The other question that we hear a lot, especially people testing out this, the graph data science library and the graph embeddings, is what happens when I restart my database? Will I still have my models? And I think I can answer that one, that right now, the graph models aren't persisted in the graph analytics workspace, but very shortly they will be, especially for those on the next version. And we're expecting that to be coming in early 2021. Anything else there that you want to add, Alicia?
Nope. In 2021, January, February, we'll have persistent and shareable models. So that means not only will you be able to keep your model, so I restart my database, my model's still there. You can also share it with other users on the same database. So if you're working in a team, it makes life easier.
Thank you very much, Amy. Thank you, Alicia. And also thank you to our audience for joining us today. Bye-bye and stay safe.
Thank you.